this is Lori and welcome to my project on using an analog to digital converter to make a dimmer for an LED with a Raspberry Pi and Python. In this project we'll use a potentiometer to be the dimmer for the LED, and we have to use an external analog to digital converter since the Raspberry Pi does not have one built in. This is the circuit I used in this project. Here's the Raspberry Pi with a ribbon cable connected to a GPIO extension board that brings the GPIO pins onto the breadboard, making it easier for setting up the circuit. Next you'll see this is the ADC chip that I used in this project. It comes from a Sunfounder kit that I've been using in Paul McWhorter's Raspberry Pi class. Here's the potentiometer and the LED and current limiting resistor. So most important first thing to do is to establish the power and ground rails. So I have them coming off the Raspberry Pi and then a crossover so that both sides of the board have power and ground. Then the LED, we'll have it grounded on the one side, and then it has the current limiting resistor and then a connection back to a GPIO pin to do the control of the LED. Here's the potentiometer, and it has connection to power and a connection to ground, and then the middle pin connects into the ADC chip. Now you can see that the ADC chip has a little bit of a complicated wiring scheme, and we'll talk about that more fully on the next slide. Here's some information about the ADC I'll be using in this project. It's ADC 0834. It's an 8-bit successive approximation ADC. And successive approximation is the way in which it determines how to return a digital value to you from the analog signal. It's 8-bit, so that means it'll return a value between 0 and 255. Here's a picture of it, and you can see this is the pinout as well. There's these notches on these kinds of chips, so you can figure out which pin is which. So the notch here will tell us that pin 1 starts here and then it goes around. And you can see, so here's the actual one, and so then this is pin 1. So that's how we know how to connect it up. It has 4 channels. We'll be using channel 0 for this project, and it runs at 5 volts. The Raspberry Pi runs at 3.3 volts, but the Raspberry Pi does have a 5 volt GPIO pin, so we can power the chip off of that, and you can see that in the picture of my actual circuit there. You need a driver to use this chip, and the Sunfounder kit that I'm using in Paul McWhorter's Raspberry Pi class, they provide a driver for Python, so go ahead and use that. And if you do use that, you do need to stick to the connections that are hard-coded in that driver. So now we'll talk a little bit about how to connect it up. And so we'll focus over here. You can see the potentiometer here in the picture, and you can see the wire going into the 3rd pin of the ADC, and that's channel 0 right there. Next we'll talk about the power and ground connections. There are 2 grounds that need to be connected here at pin 7 and pin 8. Next one I'll talk about is this power connection here at pin 9. That's the reference voltage that's used by the chip, and that figures into how the chip figures out what to return to you. So we'll see that that reference voltage is important, and you can see it's coming in at 5 volts, so that's also important. The other 2 power connections are here at the top of the chip. Pin 1 and 14 also need to be connected to power. Then for the driver, we'll need to connect up the chip select pin. That's pin number 2 on the ADC, and that needs to be connected to GPIO 17. And so if you come over here to pin 2, you can see the white wire going up to GPIO 17. Then we'll need to connect the clock pin here at 12 up to the clock pin on the Raspberry Pi, and that's GPIO 18. And so here, this blue wire here, you can see connecting that up. And then last are the data in and data out pins, and they need to be connected together, and then they are connected up to GPIO 27. So that's it for the connection. Next we'll talk about successive approximation. So I watched a lot of YouTube videos and read a lot of documents to try to figure out what successive approximation was. And I'm not an electrical engineer, so I now have just a really basic understanding. But this diagram seems to be the one that made the most sense to me in understanding this. First off is you have your input voltage coming in this case from the potentiometer, and the ADC samples that voltage and holds on to it. And then it comes into this comparator, and a comparator takes an input voltage and a reference voltage and responds back to whether the input voltage is higher or lower than the reference voltage. So that's how it starts to figure out what the input voltage is. But this doesn't just happen once. In an 8-bit, it happens 8 times, and the control logic, the successive approximation register, and this digital to analog converter actually change the reference voltage several times to try to figure out what this input voltage is. And successive approximation is the algorithm that's used in this chip to do that. So it's pretty interesting, and it all happens very fast. So for humans, it seems like it's a slow process, but for the chip, it's very fast. So let's go on and try to understand how that loop works and how the reference voltage is changed to figure out what the input voltage is. So I found that it was very interesting to try to understand how this worked, and one of the best ways I saw that it was explained was kind of a guessing game. And so in this game, I'm going to have a number between 0 and 255. So you can think of me as the input voltage. And then you can be the ADC, and you need to figure out what number I have. And all I'm going to do is tell you whether the number you guess is higher or lower than my number. And just like the ADC is using with the comparator. So if you think about this for a little while, I think you would figure out what strategy you should use. What would you guess first? So a simple way to deal with this is to say, well, let me guess something in between the two, and then I'll be able to eliminate a set of numbers based on that, and then I can keep trying a strategy like that till I get to the right number. So yeah, it's exactly what you should do. You should guess the number in between 0 and 255 and keep going until you get to the right number. So if your first guess is 128, halfway in between, I would respond because my number is 23. I would say, no, it's lower. And so now you know that anything 128 or above is not possible. So you've eliminated half of the range already in just one guess. And so I would say lower, and actually I would respond to you in binary with the number 0. And so that's a good strategy. So now let's try that strategy again. So you say, okay, now I know it's between 0 and 128, so I'll guess halfway in between that, 64. And I'll respond back to you, it's lower, and give you a 0 in response. So again, keep the strategy up, go to 32, still lower, get another 0. Go further, and then you guess 16, halfway in between 0 and 32. And now I say it's higher or equal to, and I give you a 1 in response. So now you know it's in between 16 and 31. So you're going to guess halfway in between these two, 24, and I'll tell you, well, it's lower, and give you a 0 in response. Well, now you've really narrowed the range pretty significantly. So next guess would be in between these two. So you go to 20, and I say, well, it's higher or equal to, and give you a 1. Now we're really narrowed the range pretty close. You don't have many other options left, so you go in between again, and you get a 22, and I say it's higher or equal to that. Well, now you know it's either 22 or 23, can't be 24, so it's one of those two numbers. So your last guess, number 8, is 23, and I tell you it's higher or equal to, and respond with a 1, so you know for sure it must be 23. And so here's the responses, all in binary, and if you line them up, in binary it comes out to 23 in decimal, which I kind of seems like magic, but it's just really cool math. So I really enjoyed how that worked. And so just to kind of bring this home, now you can see that what's happening is it goes through, because it's 8-bit, it does this 8 times, and it keeps changing this reference voltage, just like your guess. It keeps, halving or going in the middle and using this digital analog converter to give the proper reference voltage back into this comparator. And then it holds on to each response, 0 or 1, and it returns at the end of that the binary number, just like we did in our guessing game, and that's the value that you get back out of the ADC. So pretty interesting and very cool algorithm. So now we'll talk a little bit about the code that I used in this project. So let's go through the code for this project. First thing we'll do is import the needed modules, so the RPI GPIO module, and then the ADC driver module here. And then we'll also use the sleep function from the time library. Next, we'll set up the board numbering system using BCM, and that's because the ADC module uses that same numbering in the extender board as well, so it's convenient to use the BCM numbering system. Then we'll go ahead and kick off the analog to digital converter, and I'll set up a variable for a short delay time to use in the while true loop. Then we'll set up the LED, put it on pin 16, GPIO 16, set it up as an output, and then I created a variable to keep track of the duty cycle as we change it with the potentiometer. And then we'll set up the LED to be a pulse width modulation object, since we're going to adjust it, not just have it on and or off. It's a frequency of 1000, and go ahead and start it at the current value for the duty cycle of 0. Then in a previous project I talked a lot about how LED brightness is perceived nonlinearly by us. A linear scale doesn't quite work with it, so I wanted to see how that would work with the potentiometer too. So I did a scaling with a linear change when we turn the potentiometer, and then a nonlinear change as we turn the potentiometer. So the user can choose which way they want it to work. So we'll get to compare those two when we run the program. And here's the while true loop. So first thing we'll do is read the analog value, and then we'll change the brightness of the LED based on which type of change we selected. So with the linear change, we're just going to convert the 0 to 255 scale into a 0 to 100 scale and adjust it by the appropriate linear analog value we get. So that's what this equation does here, and then go ahead and change the duty cycle to the current value we want. Now if we've chosen to do the nonlinear change, I have some description here about how I've done that, and a little bit about the equation. Also, I'll link the video that I used where I described this more thoroughly. So if you're interested in that equation and how it worked, you might want to watch the video where I talk about this. So this is the equation that'll work for our situation. And then I just go ahead and check and make sure if the duty cycle is getting really close to 100, then I'll just make it 100 so that it goes fully on. And also if it's getting close to 1 or smaller, then I want it just to turn off. So I want to be able to turn on and off the potentiometer with the potentiometer. I want it to turn on and off. So that logic there helps that happen. And then, again, change the duty cycle to the value we've calculated. I print those out just so I can keep track. And here's the delay time. And it loops through the loop as long as I haven't done a keyboard interrupt. So if I do the keyboard interrupt, then it'll kick out of the program and I'll stop the pulse width modulation object and do the GPIO cleanup. So now let's see this, this code work. So here's my circuit. So we'll just do a quick flyby. So you can see Raspberry Pi, the ribbon cable, the extender board, and there's our ADC chip, potentiometer, and the LED. So we're gonna put this little piece of paper here to make it a little easier to see the LED, and I'm going to use the screwdriver to adjust the potentiometer, and we'll go ahead and kick the program off here and click it on, and here's where you can see that we'll be asked for the linear and nonlinear change. So let's do the linear first, and you can see it's giving us the printout, and we'll come down here and give it a try. So we're fully off. Go ahead and just turn it on. You can see it come on. And we'll just turn it slowly. And getting pretty far. And even right now, it's hard to see much of a change. You can see we're at about 50% of the duty cycle using the linear change. So it's kind of hard to see much more increase, even in person, as we go all the way up to the max. Maybe a little bit, and here we are at the max. So now we'll run it with the nonlinear change. And so we'll choose a 2, and then come down and take a look at this. Screwdriver in there good. Alright, and tweak it just barely. Just comes on. I'm trying to do kind of a smooth flow. And in person you can really see it changing almost the whole way. Maybe not once I get to the max too well. I'm just going to go ahead and take it back down really slowly. And you can see it come off. So I would say, it seems like either the linear or nonlinear scale works fine because you have a lot of control over the potentiometer, so I'm not sure it really matters too much whether you do the dimmer in a linear or a nonlinear scale. I think you can adjust it pretty well and get the brightness perhaps you wanted. But it was fun to try the 2 different kinds. So thanks for watching, and talk to you again next time.